Yeah.
Is that argument special to PA? Or
No,
can it be
no.
any recursively axiomatized?
Yeah.
So it's ZF with it.
Ah.
Right, so we know.
No, because you have to be able to carry out the consistency proof of the theory
Yeah.
in that. So.
Right, okay. So you do.
Oh, sorry, I should have said plus epsilon zero transmitted induction.
Okay,
Yes. I mean, so you need epsilon zero transmitted induction on primitive recursive properties plus sigma 1 induction, and then in that system you can, of course, not, you have to be able to carry out the consistency proof. But I mean, that's a concrete system that you then know that the proof is proven.
Yeah. Now, whether we can get there's two things going on here. I keep mentioning Fermat's last theorem because people like to talk about Fermat's last theorem, but the other is the proofs themselves, the proof techniques. It would be nice to get these proof techniques understood at a lower level. That's the kind of thing that might relax someone like, say, Milne, who promises not to use the word topos, and get to say, well, you use it when it comes up, you know. Because these techniques as a whole are not logically strong. You needn't worry that you're making some huge commitment by using them. So I think that general project on the proofs, it has two things to recommend it. One is that general conclusions are worth having. The other is it's our best hope right now for showing that FLT is provable in PA. Because of course we don't know that nobody tomorrow will announce a 5-page calculation proving Fermat's last theorem. Don't bet on it. But we don't know it won't happen. But even if they do, cohomological number theory will still deserve logical analysis, because that will just be Fermat's last theorem. So the general points are to be explored. But yeah, I don't know, what are the odds that will show that Fermat's last theorem can be proved in counter arithmetic plus epsilon zero induction? It doesn't look, I don't know if epsilon zero induction is going to be real helpful in approaching these proofs.
No, that's what you need in order to prove consistency.
Yeah.
Hilbert's proof
Yeah.
is, if you have a whatever kind, a finitary consistency of a proof in a given system of the consistency of the strong system, e.g. PA, if you proved it in PA, or if it was ZF, but that we don't have interesting consistency proofs for that. But then Hilbert's general argument, which he actually formulated specifically in terms of Fermat's last theorem, as it happened, was that if you have a proof in this infinitary system, then from the consistency proof, you can generate a proof in the weaker system, in the proof in the system in which you gave the consistency.
Because it's pi01 statement.
Yeah.
Mm-hmm.
Because basically you need provable sigma 1 completeness plus sigma 1 induction.
So if I'm understanding you, the point is that we will need to believe in epsilon naught induction to accept this reasoning. Sure. But the reasoning will convince us that somebody who didn't believe it.
But apply just to primitive recursive.
So this is the kind of thing that happens in proof theory. We now know there's a proof in PA, but we don't really have insight into the proof in PA. We have insight into the proof in a stronger system that we happen to know is conservative for this kind of statement. Now we have a lot of insight. I mean, Hilbert's argument is enough to, you might be able to get rid of the assumption of epsilon naught induction. This might give you a guide where you can actually find a more direct argument for proof in PA, or it might not.
Well, but that wouldn't go by this means. This goes via consistency proof of the infinitary theory. And we know that can't be done for anything weaker than epsilon zero. Epsilon induction on primitive recursive properties or predicates.
The other thing is that kind of argument won't address the thing that I get from people in number theory that I'm interested in addressing. That the proofs are just arithmetic as they stand. That what you're thinking about when you give this proof is pretty much arithmetic. Now you're giving some reasons why we should say, not first order arithmetic all the time. Yeah, well, but I mean, you're giving examples of steps that aren't going to reduce that directly and that occur in the proof.
No, I was just worried about
Yeah.
if statements.
Yeah, yeah, yeah. Yeah, I mean, I certainly don't know how this is going to come out. I have to say I don't know how it will come out. But these are the directions that I can tell you one thing that will come out. The proof techniques as they exist in the EGA and SGA can all be done at the strength of simple type theory with infinity. That's actually known. Grothendieck universes are known to be radically stronger than is needed. And those proofs are given almost without alteration. Like, as a good slogan, you alter the appendix on universes in SGA4, you don't alter anything else. Everything else still works for that new appendix on universes. But that's simple theory of types. That's something a lot stronger than you probably need for this number theoretical conclusion. Okay, well,
Yeah, any further questions? Or?
I do have like a sort of trivial one, right? So I think at one point you said something along the lines of this commutative law. Okay, it's sort of uniformly verifiable for integers, but it might not be concrete in Hilbert's sense as it stands, and it sounded to me like you were saying it might not be concrete in Hilbert's sense. Do you want to elaborate?
no, for Hilbert, this is a concrete plane, and this is not. Because this quantifies overall natural numbers. This is merely schematic. Take any two natural numbers, this will turn out to be true. That's why I said something like Hilbert's idea of contentual mathematics. I'm certainly not committed to saying that you could spell this all out rigorously. But you can quote it from Hilbert. And I think it's an important perspective. I think it's a perspective worth understanding.
So you didn't mean to say, or you don't think that in Hilbert's sense this thing isn't concrete until you've given an explicit bound on the length of the verification.
No, I'm trying to explain what I think makes him feel that this kind of thing is concrete.
Okay.
You not only believe it, but you see how it would happen in a generic case.
Yeah,
Okay.
thank you. Thanks. Thank you. Well, I haven't run this by you, but we usually go across the road for a beer. Yeah, so, yeah, people would like to meet in 5 or 10 minutes in the foyer, and